Good day, everyone. Today, we are getting an example of how your senior project should look like. And this is not only showing you what it should look like, this is the do's and the don'ts of what to do for your final project. I know I brought this to you guys a little bit. Oh, it's just a week, but I promise you, you're going to get it done quick because once you're done with this, you have finished the statistical course. I make sure I update the grades, make sure you know you'll find the grade. You can go on by your business. All right. Also, in this template, once you execute these skills that was taught to you perfectly, I guarantee you, you will be able to go find a job making pretty good money. Not pretty good, very good money doing this. All right. And I will honestly say it's been a joy teaching you these statistical skills, which is the reason why I chose to teach. But my teaching days are not going to be ongoing. I was at some point retired from teaching and to go into doing this statistics full time. All right, my people. In this presentation, we're going to pay attention to what John Doe did in my class in terms of the U.S. biomass energy consumption. So this is what John Doe did in my class, so we're going to follow the example. And of course, we're going to go through all these examples, each part of his presentation. Now, I'm going to present the presentation like I am John Doe. I'm going to talk like him, I'm going to sound like him, do all of that as if I'm the student. And then towards the end, you're going to see how I graded the students' work. All right. All right. This is John Doe's presentation. All right. All right, everybody. I am going to do my statistical research on biomass energy. All right. Let's go ahead and get into my introduction and my objective. All right. Biomass is a renewable organic material that comes from everybody, plants and animals included. Biomass could be a liquid, gas, or a solid. Biomass provided about 5% of the U.S. energy in 2022. Biomass, however, is harming our planet, such as global warming, deforestation, like what's going on in Brazil, land degradation, and degradation means, scrapping the land for its values, minerals needed for us to survive from, water pollution, and biodiversity loss, meaning that we clear out land just to build more and more things on top of it. The world is working to change their methods of biomass energy to reduce issues that plague our planet. And this is a pretty much of a system of the types of biomass energy we deal with. Sewage, I know, right? Weird, isn't it? So when we go to the bathroom and when it goes down to the sewer, all that, that's, permitted some type of gas which promotes energy. Trash and garbage, ew. Animal manure, wood, meaning photosynthesis. Crops and all agricultural residue, oils and animal fat. So even bacon fat, burger fat, you think of any kind of fat that we use in cooking, grease, all of that, there is types of biomass energy that we use to make energy. The objective, Does a relationship exist between biomass usage and time? How would I answer this question? Well, the question being answered. Desmos will be used for visuals, Google Slides for supported visual, TID for calculator, descriptive statistics will be used, polynomial regression will be used to answer the question and deal with the average rate of change. Now let's go ahead and talk about the data. The data has come from biomassdiversity.gov. That is where the data you see, this is where the source of the data. So this data talks about the time since 2001 and biomass consumption, which is measured in the trillions British thermal units, which is called BTUs. That is how we measure the biomass consumption. That's the measurement. All right, the methodology that will be used. So first and foremost, after collecting the data, we put it in the frequency table. We put in the frequency table to look at clusters, gaps, and peaks. If I'm looking at this frequency table that we use from Desmos, there's no peaks because everything is at the height of 1. It is clustered, from the 2000 all the way up to approximately 3500. But from 3500 to 3900, you have this big achievement. You have this big old gap here. Also, well, the biggest gap is from here, but you also have a secondary gap that is almost the same size as that from 39 to about 43. That's the smallest gap, but it's not. The data does not have the biggest. The data has the biggest gap from 30, about approximately 3,500 to 39. So that's where the gaps come. That's where we speak of the gap. Other than that, the data is pretty clustered up together. All right, so when using the TI-84 calculator to do our one variance statistics, we realize the mean of the BTU usage of energy consumption is 3,483, which of course, because we're dealing with BTUs, we're gonna round it up to 3,484. We could round it up to 3,500, but the measurements require for it to be round to the nearest tenths. So because the A is at the tenth value, we round this up to the next integer. All right. The standard deviation, which tells us the cluster or the spread of the data, and because your standard deviation is 630, which is much lower than the average, that's pretty much summarized what we have studied earlier about the data being clustered up. In which, if we go look at the table again, you will see the data are pretty much closed up together. The observations we studied was 12 observations. The minimum, the smallest amount of BTUs was 2,000 622. All right. The median, not the average, but the median was 3,380, and the most consortia was used at 4,421 BTUs. All right. So the next thing to really answer the question even further, we was looking at relationships, but using what was taught in class, we had to, determine the relationship based off polynomial regression, which is used to determine relationships by using polynomials. So when we go to a polynomial of the first power, which is known as a linear function, we realize that the R value, which tests our correlation relationship, is at 98. So 0.98, which because it has 5, we can run out to 0.99. Now, because we are looking at the R value tests the strengths of our relationship. So the closest to 1 it gets, the more perfect the relationship get. And the correlation is between +1 and -1. So if all three of these are closest to +1, which they are, that means the relationship is going to be strong and a positive relationship. But if the R values was negative for each polynomial, then it would be a declining but still strong relationship. So let's look at it. So we did the linear function, which is run out to 0.99. Well, 0.98 in this case. But if we look for the quadratic, it is going to be, and a quadratic is a polynomial with the exponent of 2, so that is 97. Alright. But if we look up here for the cubic relationship, we get 98.7. So although this is very similar to the linear function, but if you look at these R values, 0.987, both these are 0.98, but because you got 90.987, which is 987 thousandths versus 985 thousandths, therefore the relationship is strongest when your model is a cubic relationship. So therefore, this is a cubic relationship. And it's very strong and it's positive between energy consumption and years. So we look at our parameters to create our model. And A is going to be this value, negative 2.41 hundredths. B is going to be 49.5089. And then C is going to be negative 107.41 thousandths. And D is going to be 279,007 hundredths. Now, the beautiful thing about this, and when we look at the parameters, we want to round those to the nearest hundredths. So that means we want to round when it's here. So we look at B, we realize because it's 508 thousandths. Again, I'm not worried about the 9, but I'm worried about that 8, which is at the thousand place. I can round the hundredths to 51. And because, if I look at C, 1 is in the thousands place, I keep it at 400ths. And because there's nothing else here for D, it's going to be 74 hundredths. So with that being said, I could create my model with the parameters I have here and round it to the hundredths place. So this is the plot to show us this is a cubic relationship. As you can see, all these dots pretty much form the shape that we needed. And there go the model right here. Again, we use this model. We created this model based off the parameters from decimals. All right, this is where we got our model from. All right, the average rate of change. The average rate of change, what is used for, especially in this case, it became more interesting to see the amount of energy consumption BTUs being used daily throughout those years. Because we already found the average of it being throughout per year, we actually wanted to do it for the months per month. So when we look at this and we substituted the boundaries, because the boundaries from 2001, which represent 1, from 2012, which represent 12. And all we did, we went for the largest value minus the smallest value over the smallest minus the largest value. So 12 minus 1 is in the denominator, the months. And we use our regression model here, and we substituted the 12 and the 1 to subtract to find the average rate of change. Now, we know that when we come to a cubic function, this is the best way to find the average rate of change, which is another word for slope, proportions, and all that particular language. So we realized monthly there was 158 2200s BTUs used monthly throughout the US. All right, predictions. So we used the regression model that we created, and we picked out from years to figure out the consumption usage of energy. So here, for number 1, we use negative 20 because it subtracted 20 years ago. So negative 20 is 20 years ago. So we started in 2001, right? This is what we started off at. So because it was negative 20, so if I subtract 20 years from that, that is going to be 1981. So in 1981, the U.S. consumption was 217,464. Well, we'll round it out to 65 BTUs of energy being used. All right, so the 0 represents 2000. So in 2000, it dropped. It went to 2,719, well, 720 BTUs. All right. The 14, that's just coming from at 2014. This is the BTUs amounts. So you notice that at 2014, that's where it start declining because we're using yet less. Okay, so if we look at 2024, we see it decline again. And then in 40 years from now, so that's 2039, you're going to get a bigger decrease. So all this is telling us, in terms of time, energy consumption will decrease. All right. So this right here is just a prediction of biomass consumptions in terms of the time. So here we are. So the Y again is just a consumption of 50. 500s represent the consumption, which is 500 BTUs, 2000 BTUs, 5000 BTUs, 5500 BTUs. And we're going to go to the graph and see when this happens. So basically, when the BTUs are at this number, we try to figure out what year would the BTUs be at 50, would the energy consumption be at 500 BTUs, when it becomes 2000 BTUs, etc. So when we look at this, we see what we're looking at. So when it's at -4, that means it's 4 years from 2001. So that means that when our energy, again going to the colors that we posted, was at 1996. So 1996, our energy consumption was at 50. And it's just this is pretty much just that. So these are just telling us the years. So again, we notice that throughout the years progress, the consumptions being decreased. So let's go into the further details. So from the data we just pulled and analyzed to using the TI-84, the lowest biomass energy was at 2,622 BTUs. The average was at 3484 BTUs. And then the maximum was at 4421 BTUs. And then the lowest amount took place in 2001 and the highest at 2011. And the data was clustered from 2007-2008. And this is our descriptive statistics analysis. All right, so using our inferential statistics, there is a strong relationship between years and biomass energy consumption. The relationship is a cause and effect relationship. For every year passed, there is 158 2200s BTUs used monthly. I'm sorry, I wasn't daily, it was monthly. Because that's why I was trying to look for the average rate of change monthly throughout those years. According to our model, as the years go by, the energy consumption decrease. Our model helps us realize that in the 20th century, the energy consumption was used the most. But in the 20th century, 21st, that's where it decreased. All right, now let's summarize and conclude. So average biomass consumption, the average was at 3484 BTUs. The lowest amount took place between 2001 and the highest 2011. The relationship of years of energy consumption is a cause and effect relationship. Biomass energy has been reduced due to combating global warming. Our model predicts that energy consumption will continue to reduce throughout the years. Reducing energy consumption will benefit the planet if various sources are used. Yay, he finished. Okay, all right. Thank you, John Doe. That was a interesting presentation. I learned something about it now. I want to know more about biomass consumption. And who knows, maybe I'll be careful with my trash usage. Alright, so this is how I graded the students' work. So, this John Doe did use his statistical skills accurately. He gave me what I needed from him. He gave me mode, median, all of that. Then he demonstrated the usage of regression. He used the technology flawlessly. The student did use correct language. He did not use I, we, or nothing like that. And when he did it very minimum. So it wasn't like okay. It wasn't I this, we. No, don't do all that. However, well, I enjoyed this presentation. The presentation was clean. It was organized. It wasn't a whole lot of words on a screen. I was able to read it in terms of the bullet points. It transitioned perfectly. So I really enjoyed that read. It was original. Now, the only issue that I have, the student didn't fully apply the definition of statistics. So here's what this student did not do well on. So we know that statistics is telling the data to make a change. So when he was talking about, you know, how biomass energy, mess with the world in terms of water pollution, deforestation, and all the other stuff he mentioned, there was no statistics behind that. So his point was, is there a change? Was there a relationship? Cool. But what was the point that he was trying to make? I mean, why I understood was he was trying to advise us to be more cautious about our trash and not, relying so much on consumption energy. But if he would have had the statistics attached to that, it would have made the point better. He did apply it to a certain extent, because we realized as the year progressed, the consumptions did decrease. And it makes more sense because of the whole global warming issue. That really, helped a lot. But I felt if he would have used more, if he would told us more about the energy, types of energy, which he did in the beginning, but told us in detail about it. It told us mainly more about how the energy was polluting the environment, the statistics behind that. He would have scored higher than a 75, and therefore a 75 occurred. Everything else was done nice, but it is imperative when you're using statistics, you have to make your point across. He did do it, but it wasn't strong enough. It could have been stronger have he would have, have some statistics about the global change and the whatnot. But, but, even though he now used that definition well, he still proved the point that when we reduce, or a point that's saying that the energy consumption was reduced due to people changing their minds about climate energy. So that was the only good thing that came about it. I wish that there was more statistic behind that to make that a bit stronger because again, you are making an argument. Statistics is to make a change, make your point. Without you making a point, without telling some numbers, guess what? You cannot make your point across. The regression did help because it showed the relationship. So it did that part. But again, he needed to be a little bit stronger about the climate change or included a little bit more statistics there for the point to be across. Alright, y'all. So that's pretty much just it. These are the do's and don'ts of your project. what to do, what not to do. If you have any questions, of course, come see me.